Hello and welcome. In this video, we'll be discussing the chemistry of gallium and the organogallium compounds. In this slide, we should discuss gallium and its properties, specifically in relation to the periodic table. Here we have a lovely coloured periodic table, and it shows us here where gallium is. It's in the icosagens, or group 13. It lies here in the fourth period. It is also a metal and in the P block, hence why it is in red. This here is the P block of the periodic table. We have the D in purple, and these different colour blues we have the S's. Now the P and the S, they're the most relevant, as these electrons will affect the oxidation state of gallium. Gallium can lose this one P electron, and it will form gallium plus 1. However, this is the least common of the two oxidation states. It's much more favourable for the gallium to lose this one P electron and both of these S electrons. It will then have a filled D shell at D10. In some cases, gallium-1 does form, but this is mostly with gallium monohalides, for example, gallium bromide. Gallium's melting point is different to those of the metals close to it, such as zinc and aluminium, as its melting point is only 30 degrees Celsius. It does share some similar properties with aluminium in structure, hence why it is able to affect aluminium's structure if it seeps into it. It can also form 3,5 semiconductors. The best ones it forms are with gallium and arsenic, and gallium and nitrogen to form gallium nitride and gallium arsenide. Here we shall discuss the preparation of organogallium compounds. The first preparation, we can use gallium chloride and an alkyl lithium, or other types of organolithium compound. Here we use Bule or butyl lithium in 3 equivalents. With the gallium chloride, we then fully substitute all the chlorides that are on the gallium, and chlorides go to the lithium. We use a benzene solvent for this reaction, and here we can see the tributyl gallium. We do this at minus 78 degrees due to the Bule. If you do it at higher temperatures, this reaction is not going to work, and anything lower will be slower. We can also use a THF solvent instead of the benzene. This gives us this reaction. Here we're using a different organolithium, but this does not matter, as we still get an organolithium compound at the end. However, the THF will form this adduct. We expect this due to the nature of THF and its oxygen. However, if you could use benzene instead, you don't have to worry about this. And again, you're going to have to do this reaction at minus 78 degrees Celsius because you're still using organolithium. So why wouldn't you just use benzene? To form an organogallium compound, we can also react it with the Grignard reagent. Here we have magnesium propene, or this would be, say, bromo-magnesium propene. The bromine has not been put on here, so please imagine it is there. We again use gallium chloride, and we use 3 equivalents of the Grignard in order to have a tri-substituted gallium. Here we have propenyl gallium. We could also use different equivalents. As I've stated, we use 3 equivalents here and 3 equivalents of the Bule here. This will give us partially alkylated compounds. If we use 2 equivalents of methyl lithium, lime, whatever you want to call it, again, gallium chloride at minus 78 degrees, you will get or chloro dimethyl gallium. And one thing that's worth pointing out about this here, or the Grignard reaction, is that you will need to do it in THF and potentially under an argon atmosphere. Here, using benzene or THF as suitable solvents. Organogallium has a few uses. One use is an alkylating agent. We use trimethyl gallium to methylate this carbonyl. Now, due to the reactivity of an aldehyde, specifically benzaldehyde in this case, we need to use a Lewis acid catalyst. We'll use Tickel, titanium tetrachloride in a THF solvent. If you did not wish to use a Lewis acid catalyst, then you might want to use something a bit more like an acyl chloride, as these are more reactive. But if you can do a reaction with a small amount of catalyst, I think it's about 10% in solution, or this in a solution is about 10%, then you should be fine. This is the ideal conditions for reactions with ketones and any sort of esters or carboxylic acids. Anything that isn't Tickel, such as dichloromethane or another solvent such as toluene or benzene, you'll get a lower yield. This reaction specifically will give you an 80% yield. We also have alkyl azido-gallium compounds. Here we have trimethyl gallium and hydrozoic acid. We'll then out to the other end get azido-dimethyl gallium and a bit of methane. You could use different azido agents such as azido chloride or azido-trimethylgermanium. As I stated earlier, gallium nitride is a very useful component in the semiconductor industry as a 3,5 semiconductor. This is one of its precursors. In this slide, we shall talk about gallium semiconductors, specifically one being gallium nitride. It's better than silicon, as stated here, as it has a band gap of 2.3 electron volts more at 3.4. This makes it very powerful and can be used as a very good light emitter, specifically white light. You'll notice the street lights that we get around now, much more efficient, much brighter, possibly distracting whilst driving. White light contains all the other colours, even violet, which we can use as a violet laser diode. Now this is used in Blu-ray disc reading, potentially where the name comes from. Lasers can be seen as rays, violet, similar colours to blue, potentially Blu-ray. Gallium nitride's downside is that it cannot operate at higher temperatures, unlike another gallium semiconductor, gallium arsenide. Semiconductor works at such high temperatures that it was first used on the Vernier 3 probe to Venus by the Soviets, where it would have to operate as a solar cell at 464 degrees Celsius. That's just back in 1965. It was also successfully used on the Mars rovers Spirit and Opportunity, so it does very well in space. Gallium arsenide holds the single junction record for semiconductors as of March or February this year at 30.5%. It broke its own record from the previous year, 2019, of 29.1%. Thank you for listening to this presentation on gallium, its properties in relation to the periodic table, organogallium, synthesis and reactions of organogalliums, semiconductor usage, specifically gallium nitride and gallium arsenide. Thank you.